Good morning, everyone. I'll talk about our work on natural language object retrieval. In this work, we approach the following task. Given an input scene and a natural language query text, we want to localize the corresponding target object in the scene. For example, given this or-door scene image and a query text, window upper right, the goal is to localize the corresponding window in the image with a bounding box as shown in green. Also, given another query like bottom left window, we would also like to localize the corresponding window. And this is a task that traditional object detection method cannot solve, and one has to comprehend the query text in order to retrieve the corresponding object. This task is related to but also different from several other multimodal tasks, including image captioning and text-based image retrieval. In image captioning, description texts are generated for the input images, and in text-based image retrieval system, an image is returned given a textual expression as query. However, both these two tasks operate over whole images, whereas the natural language object retrieval task that we address in this paper operates over regions in one single image. Given an image and a textual query, a bounding box location is returned as retrieval results. This task can be seen as a grounding problem, where the given textual phrases are grounded in an input image. And our paper is also related to Junhua Mao's talk on Monday about generation and comprehension of object descriptions. Now, I'll talk about the method we use to address this task. In this work, we propose the following pipeline for natural language object retrieval. Given an input image and the query text, first, a set of bounding boxes are extracted from the image as candidates. In our implementation, we use object proposal methods, such as edgebox, to obtain the candidate boxes. Then, we score the candidate bounding boxes according to the natural language query, using what we call a spatial context recurrent ConvNet, or the SCRC model, which I will talk about later. And finally, the highest scoring candidate bounding box in the input image are returned as retrieval results. As you can see, the most important step in the pipeline above is how to score the candidate boxes according to the query. We define the score of each candidate box as the probability of the query text to be generated from that box. For example, in this image, the query text, man in middle with blue shirt and blue shorts, has higher probability to be generated from the red box than from the yellow box. So the red box should receive higher score for this query. Then now the question is, how to obtain the probability of the query text to be generated from a specific bounding box in an image? It's well known that many LSTM-based image captioning models, such as the LRCN model shown on the left, learn to predict the probability of the next word conditioned on previous word it has seen so far. These image captioning models can then compute the probability of the sentence to be generated on an input image. So it's natural to think of using an LSTM image captioning model to score the candidate regions. Therefore, a simple approach will be to take the LRCN image captioning model and, instead of running it on the whole image, let's run it on the candidate bounding box regions in the input image and compute the probability of the query text to be generated from these regions. Then, we can use these probabilities as scores for the regions. However, the LRCN image captioning model scores each bounding box region based on its local image feature only. But the regions in an image are often more related to each other than different images in a dataset. So, when considering the probability of the query text to be generated on an image region, it's not enough to only use local image features from the region, and instead, spatial propositions of each region and scene context also need to be taken into consideration. For example, in these three images, spatial propositions like left and right and fine-grained descriptions like cyclist are needed to distinguish the three men in context from each other. To address these problems, we propose the Spatial Context Recurrent ConvNet, or the SCRC model. Besides local image features from the bounding box region, we also use spatial coordinate of each box to provide spatial cues, and also we add whole image feature as scene context. This is sort of similar to using image level context feature to help object detection. In the SCRC model, we use two CNNs to extract visual features from the bounding box and the whole scene. Our model has two LSTMs on the second layer, a local LSTM and a global LSTM, that process the local features and scene-level contextual features respectively. And finally, the probability of the next word is predicted using the hidden state of the two upper LSTMs. This model can be used to score the candidate bounding boxes by computing the probability of the query to be generated on each bounding box region. However, one remaining problem is that the region-level textual annotations are more expensive to obtain, and the available data are often limited. To address this issue, we propose to transfer visual linguistic knowledge from image captioning tasks by first pre-training the model on image captioning data, which is often easier to obtain. During pre-training on image captioning, we only train a subset of our model as shown in the lower right figure to generate image captions in MS COCO dataset using global scene-level context feature, and through this pre-training, we learn a good set of initial parameters for word embedding and word sequence prediction. We then fine-tune the pre-trained model on annotated regions by maximizing the probability of the description text to be generated from released regions. Given an image, a bounding box, and the text sequence, we maximize the probability of the text sequence conditioned on the image and the bounding box. This is end-to-end trainable with backpropagation. In our experiments, we evaluate our method on several datasets. We first train and evaluate on the referred dataset, which contains referring expressions on image regions. As described before, we first transfer from image captioning by pre-training our model on MS COCO image captions, and then fine-tuning the model on referred dataset. During testing, we use top 100 Edgebox proposals as our candidate bounding box set, and evaluate with retrieval recalls. This table below shows the results. In our ablation study, even without using spatial information or scene context, and without pre-training on image captions, the vanilla SCRC architecture already outperforms the previous Caffe 7K method and also the RSCN model on this dataset. Then, after transferring visual linguistic knowledge from image captioning through pre-training, the performance is further improved. And any bounding box coordinate as spatial cues also improves the performance. And finally, adding scene-level contextual feature gives the best performance. And the last row shows the coverage of top 100 Edgebox proposals on this dataset, which is the upper bound recall of all methods using these candidate bounding boxes. Here are some visualized results on this dataset. Given the query text, the yellow box shows the ground truth region, and the green box shows our retrieval result. In this image, our method successfully localized the bird on the left, and it picked up the white hat correctly in this example. And also, window with closed curtains here. This slide has more visualized examples, showing different query expressions on the same image. And it's cool to see that in this example, that our method can distinguish fine-grained objects of the same category. In this example, our SCRC model successfully localized and retrieved the person corresponding to the queries, and also the corresponding persons in this example, and also different types of chairs here. There are also some failure cases where a given picture second from left as query, our method retrieves the picture from the left, but not exactly the second picture from left. And in this example, our method sort of gets the water in the center bottom, but does not localize it precisely. We also train and evaluate our SCRC model on the Flickr 30K entity dataset in a similar scenario, and outperform the previous canonical correlation analysis result on this dataset. Besides doing natural language object retrieval, our model can also be applied directly in another task to generate region descriptions, since it captures the probability of the text description on each bounding box region. Below are some examples where textual descriptions are generated over provided image regions as shown in yellow boxes. To sum up, in this paper, we addressed the Natural Language Object Retrieval task with Spatial Context Recurrent COMNet, or the SCRC model, which is an end-to-end trainable model that scores a candidate box based on its local image descriptors, spatial configurations, and global scene-level context. The SCRC model also transfers spatial linguistic knowledge from additional image captioning data through pre-training. This is aligned with the purpose of Lisa Hendrick's work on Monday, which also transfers knowledge from additional and paired data to help image captioning on novel objects. For more details, please visit our project page and see our extended paper on arXiv. In our follow-up work, we also propose a discriminatively trained ground R model and achieve significant improvement over SCRC, and please follow the arXiv paper below for the details of this model. We also extend the language-based object localization from bounding boxes to dense pixel-wise segmentation, by first encoding the textual phrases and then performing fully convolutional dense classification. If you are interested in the details, please follow the arXiv paper below. That's all of my talk. Thank you all for listening. If you have any questions, please come to our poster.